The second method that we learned for finding dA was to use a recipe that used the Jacobian, okay? And this is a general recipe that always works, okay? And this is somehow similar to what you do in one dimension. So remember, in one dimension, you start with dx and you want to write it using du. So what you used is, you use the derivative of x with respect to u, and you multiply by du. So by calculating this derivative, you knew exactly what to place before the du, okay? Of course, when you do a change of variables, you usually give u as a function of x. But in order to calculate the derivative of x with respect to u, you need to find x as a function of u in order to find the derivative of x with respect to u, okay? So something very similar will happen in 2 dimensions. So in 2 dimensions, we start with dA equals dx times dy. And now the recipe tells us that the new dA is going to be the Jacobian determinant of xy with respect to uv times du times dv. Okay? And I am going to do an example of this Jacobian for polar coordinates. Okay? So let's clarify exactly what does the Jacobian determinant mean in this context. First, let's remember, Jacobian determinant, when we studied about it, was when we were studying derivatives of functions that had multiple inputs and multiple outputs. But actually, a change of variables is exactly that, right? So a change of variables is changing x and y into 2 variables, let's say the polar coordinates, rho and phi, which means that for every point x and y, we have some method, some block, some function that tells us what the coordinates are in the polar coordinates, rho and phi, right? And this function is basically telling us that rho equals the square root of x squared plus y squared, and that phi equals the inverse tangent of y divided by x. Okay, that's how you can find rho and phi in terms of x and y. Now, remember that in one dimension, we needed to change from this form of the equations new variables as a function of old variables, which is this. We need to change it to put it the other way around. We need to put the old variables as a function of the new variables. In other words, we need to find the inverse operation. So the operation that changes this into x and y. Okay. Fortunately, for polar coordinates, this operation you already know it. So how do you find x? So x is rho cosine of phi, and y is rho sine of phi. Remember that all these 4 equations are very easy to derive if you remember to draw a triangle where this is phi and this is rho and this is y and this is x, right? So with trigonometry you can figure out all of these relations. So now that we have a function that writes x and y as a function of rho and phi, we can calculate the Jacobian matrix. So the Jacobian matrix is going to be xy with respect to uv, and notice that the way in which we write this is already useful because it's telling us that we need to do the derivatives of x and y with respect to u and v. So let's write the Jacobian matrix. You remember what it was? It was partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v. So remember that x and y are functions of rho and phi. So actually here, u and v, we have called them rho and phi. So let me write. Our new variables are not u and v in this case, they are rho and phi. So we simply need to calculate those partial derivatives, and those are very easy. Partial derivative of x with respect to rho is cosine of phi. Partial derivative of x with respect to phi, that is simply minus rho sine phi. and so on with the others. Partial of y with respect to rho is sine of phi, and partial of y with respect to phi is rho cosine phi. So this is the Jacobian matrix for this change of variables, okay? But what we need is the Jacobian determinant. That's why I write, so we need the Jacobian determinant, and we need to calculate the absolute value of the Jacobian determinant. So maybe I should write 2 lines here. Although I don't do this in the PDF notes, because in the books I only see 1 line. Is just calculate the determinant and also take the absolute value. So if the determinant ends up being a negative number, take the positive version, okay? So let's do it. What's the determinant of this matrix? The determinant of cosine phi minus rho sine phi, and rho cosine phi. And we are going to take the absolute value of the determinant. So this is equal to this times this minus this times this. So that's equal to rho cosine squared phi plus rho sine squared phi, which is rho times cosine squared plus sine squared, which is equal to rho. And that is how you find out that applying the recipe, dA is equal to rho times d phi, d rho and d phi. Okay? So of course it agrees with the geometrical intuition, of course. If you want to know why this is, I tried to give the explanation in the notes, okay? And I use this diagram here. So this diagram here might be, I'm going to try to explain it, okay? But it's not essential for you to understand why this is. It's enough for you to remember the recipe or look it up and apply it. As long as you understand how to apply it, it's fine. But if you are curious to know why this recipe works, this recipe basically is calculating the size of the square dA. How does it do it? Okay, let's imagine we are in the transform space. So now our axes are u and v. So each point in this space would map to a given point in the original space, right? So every value of u and v corresponds to a value of x and y. Therefore, we can do a mapping, right? So for example, this square A is mapped into this square A, and this square B is mapped into this square B. So of course, the area here is simply du times dv, okay? But the area here is different to the area here. For example, consider this A and this B. So the area in the transform space is the same for A and for B. However, the area in the original space is much bigger for B than it is for A. So somehow our dA has to compensate for that. So how does it do it? It's a very smart way. So think about the point here in transform space. This point corresponds to this point here. Now, if you move along u by an amount du, how much do you move in real space? So you have to do the total differential of your vector r, which is x and y. So how much does the vector r change when you change u? And that is given by this. So when you change u by an amount du, the x component changes by an amount, which is the derivative of x with respect to u times du, of course, right? Is the derivative, the rate of change, times the amount that you changed. That will tell you how much x changed. And how much does the y component change? It changes by the derivative of y with respect to u times du. So that will be the amount of change in the y direction. And that will give you a vector, which is this blue vector here. Okay? Next, you consider that you start at a point, u and v, and now you change v by an amount dv. So you end up here. So you are changing from here to this point here. So this change is a vector, which is given by the x component is the partial of x with respect to v times dv, and the y component of this vector is the partial of y with respect to v times dv, and this gives you this vector here. Okay? So now what is the area? When you increase this vector here and this vector here, you end up with a rectangle. How do you calculate the area of a rectangle spanned by two vectors? You can do the cross product of the two vectors and find the absolute value of that. So if you do the cross product of this vector with this vector and find the absolute value of that, find the length of that cross product, you end up exactly with the recipe, which is the Jacobian determinant times du times dv. You are welcome to try out doing this cross product and finding the norm of the resulting vector. Okay? So that is how the recipe works for using the Jacobian. Thank you very much. See you in the next video.